Ladies and gentlemen, welcome back. Today, we're going to be looking at organic chemistry. Now, this is extremely simplified. Still going to be complicated because we're not chemists. But generally, you have to do a heck of a lot of math work and science work before you even make it to Orgo. And here you're getting the crash course. What applies to us? Okay, so let's just jump into it and start looking at it. Organic chemistry is defined as the study of carbon and substances which contain carbon. In order to understand the differences between inorganic and organic chemistry, we make some comparisons. Molecules of inorganic compounds are small, contain relatively few atoms. Molecules of organic compounds are generally large and have a large number of atoms. Inorganic compounds are generally formed by electrovalent or ionic bonding, in which the electrons are transferred back and forth. Remember, they get ripped from each other, and they're held together by the positive and negative charges. Organic compounds are generally formed by covalent bonding, in which electrons are shared between the atoms. Inorganic compounds normally ionize or split into the ionic form of each individual constituent when the substance is placed in water and undergoes hydrolysis. Organic compounds do not ionize when they're placed in water. Inorganic chemical reactions between reactants occur relatively rapidly. Organic chemical reactions, well, they occur relatively slowly. Within inorganic chemistry, a major change in the molecular makeup of the reactants is necessary to produce a new substance. In organic chemistry, a minor change in the molecular makeup of the reactants can produce entirely new substances. In inorganic chemistry, chemical reactions between reactants generally result in the formation of one of only 4 types of compounds. The new substance is an acid, a base, a salt, or an oxide. Generally, that's it. In organic chemistry, you can just kind of sneeze it, throw it against the wall, and, try to figure it out. Chemical reactions can produce a minimum of 8 different types of compounds: hydrocarbons, alcohols, aldehydes, ketones, ethers, ethers, acids, amines, amides, mercaptans. This is why people day drink. Damn. Minimum of 8. Carbon. Well, carbon appears in nature in as many forms. This makes it what's called an allotropic element. When a carbon atom combines with other atoms, it shares its electrons with the atoms of the other substances to create new substances. Since carbon is the basis for organic chemistry, it creates these compounds using covalent bonds. Okay, shares the electrons, the valence electrons in its outer shell. The type of formula used to identify the constituents of an inorganic compound is identified as a molecular, or also known as an empirical formula. This is useful in organic chemistry in that it reveals the type of elements present in the compound, as well as the number of atoms each element present. A molecular formula is limited. Okay, an empirical formula is limited in that it does not reveal the arrangement of the atoms in the compound. So we know that glucose is C6H12O6, but we don't know what type of bonds, double, single, triple, is happening between them as we go forth. So even though we know the elements, we don't know their arrangement. And the exact arrangement of atoms is a key factor in identifying an organic substance. 2 or more organic substances may contain the same elements in the same number of atoms, but have entirely different physical and chemical properties because of the position of the atoms. And organic compounds like these are called isomers. So if we look at butane and isobutane right here, and we start numbering stuff up, well, how many carbons do we have? 1, 2, 3, 4. 1, 2, 3, 4. Well, crap. The big difference is we have a side chain, and that changes things. That can change things dramatically. It's because of substances like isomers that we have to create a new type of formula which reveals the arrangement of the atoms present in the substance, as well as indicate the number of atoms present. So then we get into structural formulas. It's a diagram showing the exact arrangement and bonding patterns of a compound. By using the structural or graphic formula, it is possible to show that carbon can unite with other substances in a variety of ways. Okay, so you can see here molecular formula, C2H3O2, and then you see a structural formula. So, two carbons. We have two carbons. Check, check. Do we have three hydrogens? 1, 2, 3. Do we have two oxygens? Yes, we do. Well, wait a second. We got this little sucker standing over here. Well, that's because this is part of a different type of molecule. We're going to be seeing that in the future. But two C's, three H's, two O's, and we can also see double bond here. Double bond. That would be important. Carbon can unite with as many as 4 univalent atoms. So a carbon can share 4 electrons off its shell. So in this case, we see methane, in which carbon is sharing one atom each with 4 different hydrogens. Single bond. The instant I change that, 1, 2, 3, we see a double bond right there. And then we see 2 over here and 2 there. So depending on the number of atoms that we share, we reduce the number of other connections we can take. If you can have 4, someone is sharing 2, you can only share another 2. Carbon can unite with 2 divalent atoms. So CO2. You can see carbon in the middle, and it shares 2 atoms each with an oxygen on each side. It can share, or it can unite with 2 univalent atoms and 1 divalent atom. So in this case, CH2O, we have carbon. It's sharing 1 atom each there, 2 atoms right there. It can unite with carbon atoms in a variety of ways, single, double, or even triple bonds between itself. And as you can imagine, structural diagrams can become highly complex and cumbersome. And as a result, a new type of formula was developed, the line formula. It's an abbreviation of a structural formula. It combines the use of symbols and subscripts like molecular formulas and the use of repeated symbols and bonds like structural formulas. Inorganic compounds with the same molecular formula can have 3 different isomers. Each of these has the same molecular formula but has a different structural formula. So we see here that we have straight line. We have a straight line with the side chain, and then we even have something a bit more fancy, something cyclic. There are 2 additional kinds of formulas that are used in organic chemistry, which we're going to discuss later, a general formula and the type formula. General formulas are used to identify groups of compounds, hydroxyls, stuff like that. Type formula is used to indicate the carbon to hydrogen ratio in a hydrocarbon. So folks, take a deep breath, read the chapter, go back, re-listen to the lecture, look at the slides, and if you still have problems, email me. If you're afraid to email me because I might bite your head off, which I don't know why you would, jump on YouTube. Type something in and you will see lectures about this. But again, be very careful. When you see lectures, especially in general chemistry, and you say, hey, I need to know about bonds in organic chemistry, you might have an instructor that's going to be way over your head. So when you're watching a video, if it's making you probably more confused than you need to, you should probably ask me rather than going crazy. But there's some tremendous stuff that you can find on the internet that will better help explain some of this stuff too. And if you find something like that that was helpful, share it to me so I can add it to the links in the course. So folks, we'll see you next time.